Please make sure you have your copy of the assignment Reactivity of Metals from yesterday. If you don't have a copy, it's on the cart in the folder that says this is from yesterday. So what we were doing yesterday was we were using a periodic table to label the elements in this data table and to color code them according to their being metals, nonmetals, or metalloids. So here's how our chart should look today. What the chart shows is across the x-axis the atomic number that identifies the elements, so that's how I knew how to label them, and then up the y-axis a measurement called first ionization energy. What that describes is how hard it is to pull an electron away from an atom. Electrons are attracted to the positive charges in the nucleus, kind of like how opposite polarities of magnets attract. Opposite charges of the protons in the nucleus and the electrons, the valence electrons, the outermost electron orbitals, attract each other. Now some elements react by losing electrons. Some elements react by gaining electrons. How reactive an element is going to be depends on this attractive force between the nucleus and its electrons. And that's what this axis of the graph describes. The higher you are on the graph, the stronger the attraction between the nucleus and the outer electrons, the valence electrons. The lower you are on the graph, the less attraction there is between the nucleus and the outer electrons. And that affects how much an element will react. What I asked you to do was to color code your chart to show where the metals, the nonmetals, and the metalloids were by using your periodic table. There's a stair-stepping line that runs down the periodic table that divides the metals on the left from the nonmetals on the right. And the elements that are right along the stair-stepping line have properties of both metals and nonmetals. Those are the metalloids. All of the ones that touch that stair-stepping line except for aluminum are metalloids. And so you chose 3 different colors and color-coded your chart. And what I'm asking you to do is to use that chart to answer the questions on the front. The first 2 questions down below, to look for some patterns in the arrangement of these elements. So first of all, you might notice that the metals all seem to be grouping on the bottom half of the chart, and the nonmetals all seem to be grouping on the top half of the chart. And predictably, the metalloids are right in between. So what that means is that as a group of elements, the metals all have lower ionization energies. That makes sense for metals because that's how metals react. They react by losing electrons. So you would expect them not to have a very strong attraction for their outer electrons because to react, they have to lose those electrons. On the other hand, nonmetals, they tend to be higher on the chart. They have higher ionization energy. It takes more energy to take an electron away from a nonmetal, which makes sense because of the way that they react. They react by gaining electrons. So when we look at the attraction between the positive charges in the nucleus and the negative charges of the outer electrons, the valence electrons, there's a stronger attraction in the nonmetals because they react by gaining electrons. They should have a strong attraction for electrons. Now there's one group in particular, one chemical group on the periodic table that is different from the others, and that's group 18, the noble gas elements. These are the elements that have completely filled outer s&p electron orbitals, 8 electrons, or helium with 2, completely filled electron orbitals so that as nonmetals, they really don't have any room to gain any more electrons. Also, look at where those elements are on your chart. They are all the highest on the chart. So I just circled all the ones that are the noble gas elements, group 18. It makes sense that these would be the ones that are the hardest to pull electrons away from, that they have the strongest attraction for electrons, because 1, they don't react, and 2, they already have all the electrons that they need, and because they are so strong at attracting electrons but don't have any room for more, they just don't react or react reluctantly with other elements. So these are 2 broad patterns that we can see by inspecting the results of this part of the analysis. What I'm asking you to do next is on the back of the first page to work with a partner. And one partner is going to use your chart, and the other partner is going to use your partner's chart. And I'm going to ask you to connect the dots, connect the data points for elements that belong to the same group or to the same period. So that means, looking at your periodic table, one partner is going to take the elements that are in the same periods. Periods, remember, go across the periodic table. So you would connect hydrogen and helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Connect those to make a line, or connect the dots between them, connecting the elements that are in the same period to look for a pattern. Your partner is going to do the same thing, but for groups. You're going to connect the data points for elements that are in the same columns. So hydrogen, lithium, sodium, potassium, rubidium, and so on. And then for the next column and the next one, until you've filled up all the columns from the periodic table that are on your data chart. And then look for patterns. The kinds of patterns that we're looking for we call a trend. Now, a trend you might see in this set of data here. This is annual global temperature average between land and ocean temperatures. The dark line that's in the middle is the average. And it's showing over the span of several years how the temperature is changing. And although there's some up and down movement in the chart, some years have higher temperature, some have lower temperature, overall there's a clear direction or change or trend in an upward direction. Temperatures are increasing, average global temperatures, over time. You may have heard that our president is just returning from Paris, where the United Nations had a global conference on climate change and what nations are going to do to help with this issue, because we're concerned that this trend towards warming the Earth might have some negative consequences for humans. So we're looking for trends or overall patterns. Even if there's some up and down, try to identify the trends and record those in the analysis for part 3 here. What we'll do tomorrow is we'll begin looking at the preparations for our lab, which we'll do the next day. Let's take a look at the results of your graphical analysis. So what I asked you to do was have one partner connect the data points for elements that are in the same periods going across the periodic table, and then the other partner connect the data points for elements that are in the same groups going up and down the periodic table. And so you should have your chart with lines drawn to connect the dots. Here's what the dots would look like connected for elements that are in the same group. So let me just overlay this. So elements that are in the same group, for example, group 18, helium, neon, argon, krypton, and xenon, if I connected those points and so on through the other groups that were in the data table, what we're looking for is a general trend or an overall pattern in what's happening to the ionization energy measurement, the attraction between the nucleus and the valence electrons, and the atomic number, or the size of the element on the periodic table. And when you look at it, you can see there's an overall direction. Not all the elements are going in the same direction, but overall the whole pattern, looking at for groups, is a downward trend. So that as the atomic number is increasing, the ionization energy is decreasing in a group. So that means that as you go down the periodic table in a group, there's less attraction for the outer electrons, the valence electrons. Looking at the other partner's result for elements that are in the same period, this is how it would look if you connected those dots, those data points. So within the same period, the same period, for example, period 2 with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon going across the periodic table, the overall trend in periods is an increase. As the atomic number of elements increases in a period, the ionization energy increases too. That means that the outer electrons are more attracted to the nucleus of the atom. If you were to look at the periodic table then, you could make a prediction about how elements are going to compare in their attraction for the outer electrons just by looking at where they are. Going across the periodic table, looking in periods, as the atomic number of the elements increases, the ionization energy gets higher. Over on this side, it's lower. As you go across the periodic table, the attraction between the nucleus and the valence electrons gets stronger and stronger. So it's less strong over here, and going across the table becomes more and more strong. That makes sense because as you go across the table, elements are trending towards the non-metal properties. Non-metals, as you recall, are elements that gain electrons, and to gain electrons you have to have a strong attraction for them. It's the opposite pattern when you go through groups. As atomic number increases in a group, that means going down the periodic table within a group, so as you go down in a group, the attraction for electrons is lower, the ionization energy is lower. It's higher when you're on the upper part of a group. So as you go down a group in the periodic table, elements become less attractive to their valence electrons. The attraction for valence electrons is not as strong down here. Up here it's stronger. So that has consequences for the reactivity of metals as well. Metals react by losing electrons. And so an element that has a lower attraction for electrons as a metal will be more reactive. An element that has higher attraction for electrons as a nonmetal will be more reactive because they gain electrons. Lower on the table you would predict nonmetals to be less reactive. Higher on the table you'd predict nonmetals to be more reactive. The opposite for metals. Metals you would predict to be more reactive going down a group because they hold on to their electrons with less energy. Higher in a group they hold on to their electrons more strongly, and so you would expect them to be less reactive. We're going to try to find out about this pattern of reactivity and how elements are arranged on the periodic table. In our experiment that we're preparing for, we're going to work with just a small set of metals. We're working with metals because many of the nonmetals tend to be gases and more difficult to work with, and poisonous as well. Metals are much easier to work with because they're solids, and we can put them in solutions that contain acid or water and see what happens to the reaction. So we're going to focus on a small set of elements in group 1 and 2, and then we'll also look at elements that are in period 4 to see how their reactivities compare as we go down a group or go across a period. Let me show you a quick little demonstration of just these 3 elements so that you can get a sense of how we compare the reactivities of elements as you go down a group in the periodic table. When lithium and water are combined, there's quite a reaction. The heat from the reaction ignites any hydrogen gas that's produced in the reaction, so that's why you see that fire. When you do the same thing with sodium, there's a much more vigorous reaction. So the heat from the reaction ignites the hydrogen that's being released, making quite a fireball, and it jumps around a little bit, much more reactive than the lithium was. Boom. Yeah, there we go. Take a look at that in slow motion. Just a single drop of water. Watch that again. That's pretty cool. I showed you this clip already. Potassium in water. A sizable chunk. Quite an explosion. Something that we're definitely not going to try to do in lab. So in your packet for this experiment, we are going to be working on this lab. I just demonstrated lithium, sodium, and potassium reactivity. We'll work on the other elements as well. We'll combine them with water and hydrochloric acid and make observations that we can use to compare how reactive the different elements are. And then we'll try to rank them from most reactive to least reactive and relate that to some features of the element's electron configurations and positions on the periodic table. This will lead us into our next experiment, which will look at another way that we can compare how strongly elements attract electrons.